speaker is Josh Lewis. Josh is the VP of Product at Alpine Data, and Josh is going to be talking about, now here's a word, the deplorable state of deployment. Okay, so Josh is going to set that up. Looks as if you are good to go.
Cool, awesome. Thanks, Jonathan.
Thank you.
Yeah, so my name is Josh Lewis, and my background is in academia originally. I did a PhD at the Cognitive Science Department at UC San Diego in cognitive science, looking at how people interact with machine learning algorithms, how we can make them more useful in the real world. And I've kind of taken that into industry, working at IASD and now Alpine, where I'm focused on for large enterprise customers. We work with like the banks like Morgan Stanley and Citi, JP Morgan, healthcare providers and stuff like that. How do they actually benefit from the promise of machine learning? How do they get that integrated into their businesses? How do they become data-driven businesses like a lot of the startups that we see around Silicon Valley and the Ubers and I guess Instacarts of the world, right? And one of the major challenges with this is going from the lab into production, right? Once you've built a machine learning model, how do you actually deploy it out into the real world? I think, as vendors, we've really kind of solved the problem in a lot of ways of building these models, of doing ETL and all that, but deployment itself is in a little bit of a deplorable state. And so what I'm going to do is I'm going to take you through, a proposed approach to how you might solve this problem. So first, let's just talk about the kind of technical stages of data science, right? So it's not about necessarily coming up with hypotheses and kind of the softer stuff around it, but just from a pure computation perspective, what do you need to do typically if you're starting from some data set that you've got hanging out in Hadoop or in the relational database? Well, again, typically what you're going to do is some amount of ETL, right? Some amount of data transformation, data cleansing, feature engineering, feature selection, kind of getting your data set into shape such that it can be used as training material for a machine learning model. Typically, you're doing that in batch. You're doing that with like SQL or Spark, one of these kind of batch-style technologies that can operate over kind of a massive data context. Then you do the modeling itself, so you're training some regression or some classification algorithm, or maybe you're doing unsupervised machine learning and you're building up like a clustering or a dimensionality reduction algorithm. And again, you want to do that on batch. Normally, you want to do that on kind of the largest data context available, right? So all of that's still in the lab, though. For a machine learning model to actually impact a business, it needs to be instrumented into either business processes or end user applications that the business uses, right? And that's what this deployment part is about. How do you push this thing that you've built out into the world? And so there's one way to do this that is batch, right? So maybe you have like a log of all the customers that visited your website over the last 24 hours, and then you set up like a nightly run that's going to go back and take that group of customers and do some scoring on that, like which email campaign to send to them or something like that. But there's a lot of cases where you can't do that kind of time-lagged response, and you need to do things more in real time. And that's the single sample kind of real-time deployment, deployment of real-time services, so that as soon as an individual hits your website, you can immediately determine whether you want to include them in a particular email campaign, and then take that action immediately, right? So the focus, I think, where the pain is right now is around this single sample real-time deployment. And it's important, and I'll use a customer example to kind of illustrate this. We've got a customer called Evicor. They're a medical benefits management company, and they sit in between the payers and the providers in the insurance space, basically, right? So if you're a doctor's office, you're a provider, you want to perform an MRI or something like that on your patient, well then what you have to do is you have to get that procedure pre-approved. You have to justify it, give like a medical necessity justification, and the insurance companies have rules about what qualifies for something that they'll be willing to reimburse. So the doctor doesn't want to perform the procedure without first knowing that they're going to be reimbursed for doing so. And so the insurance companies don't actually do this themselves. They farm this out to middlemen that kind of sit in between the payers and providers to make this determination. So Evicor is the largest one of these middlemen. They process millions of these pre-approval claims per month. And historically, it's been a very manual, very human process for them. So they have like an army of hundreds of nurses and around 100 MDs that, that make the determination of whether a particular procedure is medically appropriate. And so what we did with them is, this is a classic situation where a classification algorithm, a machine learning algorithm, can come in and potentially automate away some parts of this process, right? So we built an algorithm up that would basically say, is this extremely likely to be pre-approved or not? And then we put that as the first process step when a claim comes off the wire, right? Typically these claims are submitted by websites or even over the phone, right? Doctor's offices still will call up and give the details of the case, and someone's typing that into the website, right? So that claim comes off the wire. The classification is made by this model that we've deployed in real time. And if it's the case that the claim is very likely to be approved, it just gets approved, and the doctor's office gets the response immediately. If it's a more complex claim, where either we think it's likely to be denied or it's just unclear or they need more information from the doctor's office, then you bring the humans back into the loop, and it goes through that historical process that's more manual. So I think it's a great example of integrating machine learning into a classic business process, a pre-existing business process, in a way that's allowed them to grow this team of nurses and doctors sublinearly to their actual claims processing growth. So, which is a huge cost savings for them. They've saved millions of dollars doing this. So deployment is good if you can make it work. Now the problem is that you've got a fundamental tension between data scientists and ops people, especially in the enterprise, right? You've got this whole cornucopia, this like zoo of technologies when it comes to training. Maybe you're training your models with Spark or Python or R. You're doing some cool new stuff like Flink or TensorFlow. And as a data scientist, that's all super, super cool, right? You want to use the new tools, the new technologies, the new algorithms, if they're appropriate to your problem, right? You want that flexibility. And similarly, on the scoring side, there's a variety of approaches that you can use over there once you've trained the model. And the problem is that all of this is just complete anathema to an ops person. What an ops person wants is a single view of the world, a completely homogeneous set of things that they deploy, and they know how to log it, they know how to monitor it, they know that the security profile of it. It's very, very kind of manageable and well understood, and that creates this tension, right, between the ops and the data science communities in these large organizations. And so what you see happen sometimes, there's a few different things you see happen. First, sometimes the ops people get run over, and you're trying to deploy R and Python. You need all these different deployment strategies, and it's a little bit of a mess. The other thing that I've seen pretty commonly is you have a whole translational engineering team where you've got your people off over here. Maybe they're doing SAS or whatever. I've even seen like Fortran code over here that the old school data scientists are working with. And then there's a whole team of people that like translate that into Java so that the ops people just see a world that only looks like Java. And the problem with that intermediate step is that it introduces a big lag into the process. It's error prone. I've talked to customers where it's like upwards of 6 months that it takes to go from, okay, we've finished a model over here, to now it's deployed and it's been translated. And so obviously there's going to be a lot of business situations where a 6-month lag is not effective, right? So this is the challenge, and what we want to do is propose a way around this. And it's going to be based on industry standards. I'm going to drill into this a little bit. How do we solve this problem? And what are the goals in solving a problem like this? Well, first you want to be able to deploy diverse model types to the diverse platforms, right? There's whether it's cloud or on-prem, Hadoop or relational database, all that kind of stuff. You want to be able to represent the ETL and business logic, not just the scoring in a single system. So for example, if you had some algorithm that's able to predict what type of email campaign to send to this person that's hitting your website, you might also have a rule that's like, well, if we emailed them within the last 2 weeks, don't email them again, right? So that's not part of the machine learning model, really. But you want that same logic to be in the real-time system. So you need kind of a certain amount of expressiveness in what you're deploying. And then certain things like we were seeing, A/B testing and stuff like that in the previous talk, certain things like running these champion challenger style competitions, doing counterfactual analyses, like had I had this other model deployed for the past 2 weeks, what would have happened, what would the recommendations have been, and controlling the behavior of these deployed systems in real time so you can react to external events like in the financial services industry, maybe there's something that you want to react to based on like the state of the stock market or something like that in real time. All of these are things that we want our real-time system to do, right? And so what we're going to propose here is to abstract away from the complexity of particular infrastructure and compute choices, provide a very simple conceptual model that describes these services that we want to deploy into the enterprise environment, and use industry standards. I think that that's what's really kind of held us back on the vendor side here in terms of solving these deployment problems. Okay, so on industry standards, there is a historical industry standard for serializing trained machine learning models called PMML. It's the Predictive Model Markup Language. It's something that was developed in the 90s. You probably, I don't know, some of you guys probably remember that everything was a markup language. There's like VRML for virtual reality and all that, so good times. But there is a predictive model markup language. And it's got some really good stuff going for it. It's an industry standard, it's language independent, it's adopted by basically every vendor in the space. There's execution engines for these things, like in the open source world, there's JPMML. That's actually what Evacor is using to do its model execution. So it's really on the right track. But unfortunately, it's kind of like the first gen iPhone without the App Store. There's just a set of canned functionality that it has that you can pick off the shelf, but you can't extend it without updating the whole standard. And they've been doing that valiantly for like 2 decades, right? Like updating the standard and adding some new algorithms in. But obviously, if you're going to represent things like arbitrary business logic or kind of domain-specific ETL routines and stuff like that, that's not going to happen within PMML if it just has a set of canned functionality. And so the standards body behind this, called the Data Mining Group, has kind of recognized this constraint and introduced a successor standard called PFA, the Portable Format for Analytics, that really addresses this main concern. So it's still an industry standard, it's still language independent, but it's highly expressive. You can do control flow, things like for loops and if statements. You can basically express anything computable that doesn't need to call out to some external system. And also the serialization formats in JSON and YAML, which is generally easy for people to work with. So what does a PFA engine look like? Basically, it's a unit that takes some input, applies some compute, some arbitrary compute to that input to produce an output. And it also has some, some context, basically some memory local to the engine that it can use to represent state. So again, if you wanted to represent the state of the stock market or something like that, you can do that here. And you can also define user-defined functions. So if you wanted to update the context or perform some side compute, you can do that within the PFA context. So we're going to use this as one of the primitives in a system for setting up real-time machine learning services. So you have your engines that perform computation via PFA ideally, but realistically, you've got a lot of Python and R code out there. You want to wrap those as well. You've got endpoints that provide the API hooks that you integrate into for talking to applications or for kind of API or service-based integrations, and then queues that handle the communication between engines or between engines and endpoints, et cetera. So those are kind of the primitives that we're going to build up. Okay, so I'm going to try to do a demonstration here that involves like audience participation, and I found out that the Cal Wi-Fi blocks the WebSocket support, so I'm going to be running off of my phone, and I've got 1 bar, so we'll see if it works. But let's get this going here. So this is it's like a little trading game that we're going to run, where we're going to simulate the history of the Dow Jones since 1985. So I'm going to click the Start button here, and you'll see a little graph start to build up over here. And this is the close price of the Dow Jones at each of these steps, basically monthly steps. And then everyone's going to be able to get access to this little UI where you can put your name in. I'll be Josh Test for the moment, and then submit actions into the system. And then these actions are going to show up on this activity stream here. So you can buy shares and sell shares and all that. And so the goal is, I'm going to give you a URL. You can go on your iPhone or your Android phone, is to make the most money over this 30-year historical run of the Dow, right? So, time the financial crisis and all that is part of the goal here. So this is what it looked like if you get it onto your phone, and you just put your name in, and then the buttons will activate. So I'm going to refresh this here. I'm going to give you the URL for folks that want to participate. So this is it, tinyurl.com/alpinetrade. Put in like a unique name, and we'll see who's the savviest trader. What are we demonstrating here? This whole system, this whole UI, these two UIs, are built on top of PFA engines doing real-time event processing, in this case on Cloud Foundry, which is one of those kind of platform as a service style, containerized app environments. And then we'll kind of work through this example, and I'll show you how this was designed using the primitives that I was talking about earlier, and that'll give you a sense for how we can deploy these kinds of real-time services. So, okay, where are we at? Have people got their interface up and all set here? All right. So I'm going to switch over. I'm going to pray to the AT&T gods and click start. So go ahead and start buying and selling. All right, so we go. Oh, no. So the display might lag a little bit if we've got. So I think people are doing the right thing, which is to. Oh no, I think I've lost it. Okay. Well, I think I'm not going to try to pressure the connection too much here. But let's look at what happened so far. So Jeeves, I think, won, probably just by buying 88 shares in like a pretty short period of time. That's a lot of button presses. And everyone, I think, was doing the right strategy, which is obviously you want to buy in the 80s, and then the selling comes later. Oh, here we're catching up a little bit. Maybe my pocket is the magic place to put the phone. Okay, well I won't belabor this too much, but basically the idea here is that this all executes in real time with all of your guys' apps on your phones. On PFA. So let's talk about how that works. So I'm going to go back. I'll just stop this here. Go back to the slides. Okay. So basically what we've done is we've set up two different engines that are going to allow us to process these trades that are coming in from all the individuals that are using the service. The first one is going to take the trade itself in direct off the phone, price it based on the current state of the Dow Jones, which is being updated with every tick of the simulation app. And then the output of that engine is a priced trade. That's going to get fed into a second PFA engine that's going to record that trade into a ledger. And what you get out at the end is that price trade plus an account balance, how many shares you've bought, what your cash balance is, et cetera. And so when we put this all together, we're actually using those primitives, right? We have some endpoints that the applications can hook into. We have two different PFA engines for doing the compute and kind of the state storage, and then a queue that sits in between them that's kind of passing these messages along from one engine to the other. And we wrap this all up in something that we call a flow. So what this looks like from the application's perspective is you've got one application that's consuming this trade endpoint here and then getting the round trip. So when you submit a particular trade, you'll get your particular updated balance and number of shares. And then the leaderboard application is at every tick of the simulation updating the current state of the Dow Jones, but then it's also feeding off the complete fire hose of all the output coming out of the system to kind of keep that leaderboard updated live. So that's the overall approach. And I think it's representative of the kinds of things that you can do with PFA. So where are the challenges? I think, in the near term, in the enterprise especially, right, these deployments are going to be polyglot, right? You're going to be deploying R and Python alongside PFA, PMML, kind of like we have been doing, right? Like if you look at a lot of the PMML deployments, it's normally decorated with Python around the edges. I think PFA, the standard is not yet 1.0, and transitioning to it from a vendor perspective is going to be a little bit of a lift. Getting tools to export in that format and all that. And similarly with the community support, if you look at things like scikit-learn and other things that you might want to generate models that you use for scoring in production, those need to ultimately be able to generate in this other serialization format. So I think it's something that'll take a little bit of a transition. But if you look at in these enterprise environments where a lot of times the data science is falling down, it's not falling down, I think in the context of the previous talk, like in that decision science side. Like all the stuff around BI, data scientists that go off and essentially do decision support, historical analyses of historical data that roll up into presentations that they give into execs and stuff like that. I think that's functioning very well. What's not functioning as well, or what's harder for these kind of like older school brick and mortar organizations is the data-driven enterprise or data-driven products, and part of that's because they have such a hard time operationalizing the stuff that their data scientists are doing. So ultimately, I think as an industry, we need to provide a much cleaner path to production, and that's really, I think, going to have a bigger impact at companies like Evercore, where there are real business problems that we can solve with machine learning, if only we can get this stuff out into the wild. So, thanks.
Josh, great. Thanks very much. Some chance for questions. Anyone want to drill into Josh's presentation there? Yes, sir, at the back.
Do you have a sample of PFA you can? Oh, sorry. Do you have a sample of PFA you can throw up on the screen?
Let me see if I can.
Like the actual code, not like a diagram.
Yeah. Let me see here. Yeah, so here's an example of the kind of pricing engine. Let me up the font size here. So this is in YAML. So you're basically defining like an input format. Basically, there's going to be an ID, which is your name plus the action buy or sell. You have an output, which is a price trade. So you're going to have the ID, the action, and the cost. You have an initial price. The initial Dow Jones state is set to the state at the end, right? So if anyone was selling or buying before we started the simulation, they were just selling and buying at the end state. And then you have this action method. This is this primary function that's applied to the input to produce the output. So basically, we're looking at what type of action was it? Was it a buy or a sell action? And then using that to set the cost for the output, which is going to be the positive or negative of the price. And then down here, we've got that context function, that side function that's going to update the price that's stored in this memory cell right here. So that's roughly what it looks like. Now, you can write this stuff by hand, but typically what you'll see is a package like scikit-learn or something like that generating this for, let's say, like a regression model or something like that.
So who's driving the deployment at your board, or PVC's ideally driving the deployment? Is it data scientists themselves, or product managers, engineers?
I think you guys, I mean, in a large organization, you got to get the IT and like ops folks involved, right? Like data scientists tend to kind of stop caring once they've built like an awesome model that's getting like great classification rates. And so if you depend on them to be not only, I mean, already data scientists wear way too many hats, and you're like, now you're an ops engineer. Normally that doesn't go as well. So typically there's a handoff, and yeah, it's a handoff to some sort of engineering or IT or operations group. Like if it's to that translational stage, it's a handoff to translational engineering, and then they know how to deal with the ops folks. But that's almost part of the problem, right? There's not a lot of standardized process around how you do data science in the enterprise. And that's another thing we've been trying to do with our products is be a little bit more normative of like, here are the stages of data science if you're really trying to go from defining the problem all the way out to being like instrumented into end user apps or business processes. So it's pretty diverse.
Okay. Chance for one more question. Yes, just on the side here. Just wait for the mic there, please. Yeah, thanks.
Regarding to change management, how do you ensure that whatever you deploy not going to break what already in production?
Well, yeah, I think that goes back oftentimes to the A/B testing or the champion challenger models. So what we look at normally is that you'll have, once you've got something out deployed, that becomes like the champion, right? Kind of the blessed version of the model, and that's what is exposed through. You might have like a special endpoint that the champion always sits at. So if you swap out what's the champion, you're swapping out what like the applications that feed off of that endpoint are processing on. And then you'll typically run alternatives or challengers side by side with the champion concurrently and kind of measure what would happen had we used these. And if you see that you're getting better results, you swap it in. So you can kind of like dry run these alternative models, and you can also do those counterfactual analyses. Go back to a whole historical set of data and see would this new model have performed better and stuff like that. So it depends on the use case, but generally it's that kind of like A/B or champion challenger approach.
Okay.
Thank you.
Josh, thank you very much for your time. Appreciate it.